The setup for the twins paradox is as follows. Suppose I sit on Earth while you head off on a rocket ship at a constant speed for a while, then turn around and come back. We know that moving things experience time more slowly, so I'll think that when you get back, you should be younger than me. But from your perspective, the Earth with me on it is doing the moving, receding and then returning, so you think that I should be younger than you. Who's right? We'll use the fact that time rotates to sort this all out. Okay, so from my perspective, every second that passes, I stay in the same place, while every second that passes, you get farther away, and then closer. Simple enough. From my perspective, you'll take 10 seconds to get back. And since you're moving, I'll think that time is passing more slowly for you, so I'll calculate that your journey, for you, takes 8 seconds. Now, and this is the important bit, since you're moving, what you think of as the forward direction of time will be rotated relative to my perception of time. So on your outward journey, the seconds will tick away like this, and on your return journey, the seconds will look like this. From your perspective, your journey does indeed take 8 seconds. But almost immediately, we also see the solution to the twins paradox, right here. This bit of my time is unaccounted for by you. During your entire journey, you'll think that time is passing more slowly for me than for you. And indeed it is. Here and here add up to only 6.4 seconds. But because of your change in velocity when you turn around to come home, your notion of time rotates and skips right over a large swath of my time, which amounts to precisely, you guessed it, the missing 3.6 seconds. And this is the resolution to the twins paradox. Because you changed velocity, your notion of simultaneous times rotates, so your accounting of how time passes in parts of the universe far away from you will have gaps in it. Well, in reality, it wouldn't have gaps because you couldn't instantaneously change direction. You'd have to fire your rockets to start heading home, and during that acceleration, your notion of time would have very, very quickly rotated through the missing gap in my journey, allowing you to properly account for the missing time. In summary, during your outward and return journeys, 10 seconds would pass for me, and I'd calculate 8 seconds as passing for you. 8 seconds would pass for you, and you'd calculate 6.4 seconds as passing for me during your outward and return journeys, and 3.6 seconds as passing for me during your acceleration, even if it was basically instantaneous. So we both agree that when you come home, you'll be younger. And indeed, this is exactly what happens when you send an atomic clock flying around in an airplane. It records less time as having passed than a twin atomic clock that stays on the ground. P.S. The time rotations I've been talking about are actually called Lorentz transformations, and they're the way that most working physicists think about special relativity and things like time dilation, relativistic Doppler shifts, and so on. Trying to understand relativity just by using basic equations for time dilation and length contraction, like is often done in beginning physics classes, will often lead to confusing apparent contradictions, because these equations don't take into account the full changing of simultaneity of events, and so on. Hey, Henry here, thanks for watching. I'd like to thank The Great Courses Plus for supporting this video. The Great Courses Plus is a video learning service with thousands of lectures and courses from university professors, Smithsonian curators, National Geographic photographers, professional chefs, and so on. They even have courses by some past guest narrators of Minute Physics, Sean Carroll and Neil deGrasse Tyson. The Great Courses Plus is offering a free 1-month trial at thegreatcoursesplus.com/minutephysics. Again, that's thegreatcoursesplus.com/minutephysics, or follow the link in the video description.